And he's talking about molecular storytelling and materials design towards a sustainable world.
Hello, yeah. Well, thank you very much for the organizers for this opportunity, in particular to be the second one. And I'm going to try, yesterday I looked for my slides for the previous one, for the first, and I'm going to see some changes in terms of philosophy, what you have done in the past up to now. So the idea here is actually talking about how can you use materials design, in particularly looking for problems for the sustainable world. Now, to do that, you're going to try to use multiscale molecular simulations that you have seen in several of the talks here. And they're going to also introduce the virtual reality and machine learning methods in order to improve and accelerate such a design. And you have two examples. One is related to the CO2 capture and sequestration. And the second one is regarding to the gas separation in the use. So you're going to try to clean somehow what has been done on the fossil fuels. At the same time, try to use these products for a better, in a sustainable manner. Now, what have been inspired us to do so is try to actually look for these terms, the design, to be able to actually manipulate the systems in such a way that you can induce or can probe experiment for a given result. And this has been inspired on the Sustainable Development Goals on the United Nations, in such a way that you're going to try to use some of these methodologies to actually problems regarding the energy and also the environment applications from a multi-scale perspective. So as I mentioned to you in the first edition of this workshop, I mainly focus on the fossil fuels. We propose new strategies in order to enhance the oil recovery. Nowadays, you saw several talks regarding the renewables. And my role here is try to do something intermediate in such a way that you may try to solve the problem that has been coming for the use of fossil fuels over decades. Now, the point that the strategy that we're going to use is the computational design of materials. And here again, I want to emphasize the word design, in the sense that you're going to experiment and try to see what is going on in terms of what it can do actually to manipulate the materials for some applications that are of our interest. Now, to do so, what we're going to do is the combination of molecular simulations, machine learning, and virtual reality in such a way that would you like to actually be able to model a physical phenomena ranging from molecular up to macro scales. And this is in a multi-scale method. So you really want to go from quantum mechanics up to the atomic modeling, and then look the effect in a larger scale, for instance, in the scale of a device. For this, there are several problems. One is regarding that several of the phenomena that you see in the materials occurs in different scales. And also, you need to be able to make the connections between those scales in terms of methodologies. Together with that, you also you want to include the use of machine learning in order to accelerate some of the predictions, at the same time, the experiences that you'd like to do. Now, this is what usually has been shown in terms of material design. So the things that you would like to introduce on top of it, on top of to use the computational material design or science, where you can use this multi-scale approach, is to be able also to have an idea, if you want to think in terms of design, is to have an idea about to experiment scales that are far beyond our daily life. And to do so, you are going to use a combination of methodologies. to be able to do material design using virtual reality in such a way that you can manipulate atoms, see what happens, at the same time make decisions during this experience, and propose solutions for a given problem. Now, to do this kind of experience on virtual reality, it means that you have to both to be able to accurately calculate some of the properties. However, with the methodology that you have so far, this can be taken, for instance, first principle calculations can be taking hours, weeks, or months. So you're not going to wait for that for such a long time. So then you have to be able to couple this experience with some more, to accelerate such calculations. And also, if you like to do that, you're going to use data analytics. You're going to use methods that is regarding to machine learning, for instance, that is able to accelerate, but at the same time, to keep the accuracy that you have in order to predict the materials. But on top of that, you also would like to introduce the perceptive physics. It means that not only during the experience, you'll be able to manipulate the atoms, the molecules on different scales, but also you can introduce other senses during this experience. For instance, the listening or touch, smell, and so forth. So I remember in the previous workshop, I talked about the possibility to listen, the dynamics of water molecules. Now you introduce other types of senses in order to enhance this experience on material design, okay? Now, this is more or less the idea behind the methodology that you have introduced. Now, I'm going to give you some examples that is regarding the problem of sustainability. And the example that I choose here is a way that you can go for a low-carbon society. It means that you have to somehow be able to either capture, sequestrate, and also they use the CO2 in such a way that you can solve some of the problems that is regarding the sustainability goals of the United Nations. So I'm going to start then with work regarding to the capture. Now, what is the problem? No? The problem is that I would like either to be able to capture in storage and for a long, long time. And then you have two issues. The first one is to be able to capture the CO2 in storage. Usually, it is in geological facilities because you can do in large scale and also you can do for a longer time. However, there are some problems that is regarding to this. One is from the economic point of view. The other one is also regarding to the stability of this storage. And finally, this problem of long-term storage, because it's not for 1 year, it's for 100, thousands of years that you want to store CO2 there. Now, the other problem is how you're going to inject CO2, for instance. So you have the CO2, you want to avoid the CO2 to go to the atmosphere, and you want to inject the CO2 on the geological facilities. But to do so, there are two options. One is to use the CO2 with water, but you don't want to dispose water that is a very, from the natural resources, maybe one of the things that you have to worry about it. And the other point is to use the CO2 in a superfluid phase or the pure CO2. No? Then, for that, you need to think about which materials you can use in such a way to be able to capture the CO2 for this very long term. Now, one of the questions that you may think is, what actually would be the features that you needed for a good CO2, a good material for CO2 capture? The first one is you need something that it has needed a large surface area. Also, it has to be a good adsorption capability. As well, it should be able to capture CO2 selectively, because if you want to inject with water or other gases, it has to choose the CO2 instead of the other molecules. At the same time, it should not require energy on this process, because if you want to capture with energy, it means that you're also producing CO2 at the same time. So it does not make sense so much on this capture process. And finally, it should be inexpensive and also environmental friendly. So one of the materials that you have such properties is the clays. And the point here is, how can I engineer the clays in such a way that I can enhance the CO2 absorption, at the same time to be able to do this in large scale, and then finally to be selective towards other molecules that you can have it in the geological sites. So this is where a combination of experimental and also the computational methods can help us to understand and also to propose new ideas regarding to this topic. Now, the difficulty here is because if you want to have the CO2 capture in clays, mainly you need to understand what is the role of these interlayer ions on the structure of the clay. So if you have a large, this is the periodic table in terms of the ionic radii, and I choose these two examples. One is you have a large ionic radii. So in this way, you create space between the layers and allows the CO2 to get in. In the other case, for the sodium, for instance, that you have a small ionic radii, because of this small ionic radii, the CO2 molecule is not able to get in on the system. Now, recently, they observed experimentally that even the nickel that has also a small ionic radii is able to have the CO2 getting on the system. So the problem here is well, first of all, can you understand this, help the experimental ones to induce such a capture? In the other cases, particularly for the sodium case that you have is abundant in nature, can you propose ideas that can also help for this kind of clays to be able to have the CO2 capture? Now, from the experimental point of view, what you have is a sample where you can intercalate different ions. Usually, for this kind of a system that you have studied, so you are able to capture 1 ton of CO2 per meter cubic. This is almost the second most material in terms of capture. The best one up to now is the metal-organic frameworks. And experimentally, what they do is to be able to synthesize or use natural clays where you can play with the interlayer ions here. So they first inject the water on the clay, so you see an effect of swelling. Then you heat it up, then you have the water out. Then finally, you inject the CO2, and you could observe the swelling of clay. It means that the CO2 has been captured during this process. So this can be monitored by X-ray diffraction, where they can see this despacing between the layers in such a way that you can monitor if you have the CO2 getting on the system or not. As I mentioned to you, the point is, are you able to engineering the choice of the ions in such a way that I can control the amount of this CO2 that can be captured on the system? Now, to do these calculations, in the first example here, as I mentioned to you about the multiscale, you mainly have done first principle calculations using the Siesta code, and you are able to calculate the absorption energy regarding the CO2 or the water on the different surfaces on the system. And then important information is this despacing that can show you can compare and validate with the experimental data. Now, on top of that, you also are able to mapping the potential energy regarding to which will be the site favorable for this to have the CO2. At the same time, from the electronic structure point of view, if you're going to have some changes in terms of the charges, or if you are able to, by manipulating the ions, what is going on from the perspective to be, for CO2 to be captured. Now, this is interesting. This is what usually people can do. But then you can do something, go a step forward. That is to be able to choose or monitor now what happens if I change the type of the ions that you can have in the clay. And this is some experimental measurements where when you see this change in terms of these peaks, it means that you favorable the CO2 capture. Some cases you may not see it, but in the case of the lithium, the nickel, and also in some cases for large cations, you will be able to see the CO2 capture. At the same time, with the first principle calculations, you can determine what will be the distance between those layers for the different types of the ions. Look, the order of magnitude here is from 6 to 8 angstroms. And if you want to see the absorption of CO2, this number should increase. At the same time, only looking for the interaction of the CO2 with the different surfaces, you are able then to calculate what will be this absorption energy and see which of the ions will be the most favorable in competition with water. Because you need to have such selectivity in order to enhance the CO2 capture. Now, for the case of the nickel is a case interesting because experimentally they saw the CO2 capture by measuring this, the G spacing. However, they could not understand because if you only have the pure nickel ion on the structure, you cannot attend to this distance between those layers. So then it has been done a hypothesis where you have the nickel hydroxide and then you perform some first principle calculation, molecular dynamics, first principle molecular dynamics calculations, where you could see the formation of the nickel hydroxide. And you can understand now this process because in the first case, you have both the formation of the nickel hydroxide. In the other layer, you have the nickel case. With the CO2 you're going to enter only where you have the nickel hydroxide layers. And finally, you have the full absorption. And if you heat her up or if you release the pressure, then you see the CO2 leaving the system. So this is a way that you can capture CO2 in large scale using those clays. Now, what you can do better and propose for the experimental people is to be able to improve the CO2 absorption by basically changing the surface charge of the clays. So experimentally, you can do that by, for instance, the composition of the clay. You can either include it nickel, magnesium, you can change the ions that you have in the system in such a way that the surface charge that you're going to interact with the system can be changed. So you can see here the energy with respect to this distance. And those distance shows that when you have the CO2, when you have, in this case here, the nickel hydroxide, you resolve and capture the same result that you see experimentally. And at the same time, you have the CO2 absorption favorable for this hydroxide, nickel hydroxide system. So you can play with the surface charge. You are able to enhance also the CO2 capture. Now, another case that is interesting is the case of the sodium, because for sodium, it's abundant in nature. However, if you only have the sodium, you are not able to have the CO2 getting in the system. Now, what you have done was to propose some mechanisms based, again, on the ab initio molecular dynamics, where you first start with the water, then you could see this effect of swelling. Then we have the water with CO2, and you could observe the presence of the CO2 near the sodium ion, and also the presence of other systems that will be interesting for catalysis. I'm going to mention later on. And finally, the pure CO2 in such a way that if you want to use the sodium ion interlayer on the clays, the best way to propose and to promote the CO2 capture is together with water. And this is something that experimentally it has been, could be shown. At the same time, you can also play with the surface charge of the clay in such a way that you can decrease the amount of water that is needed for the CO2 capture. Now, this is part of the problem, as I mentioned. So we propose materials, natural materials, where you can have the CO2 capture. Now, one of the points that you need to do is to separate CO2, for instance, so with methane or nitrogen, whatever gas that is needed in order to inject the CO2. And for that, you're going to use non-fluidics. And this will be done in a multiscale framework where you're going to use the combination of quantum mechanics together with molecular dynamics. So what is the point here? Is to be able to propose new technologies, membrane technologies, so based on nanostructured materials. This mainly because of the low flow rate that you need to enhance. At the same time, usually the membranes that you have nowadays is occupy a huge area on the industrial plant. So if you have the nanostructured materials, then you can have a compact design in terms of this membrane. At the same time, it can be more efficient. And this is more or less what we're going to try to do, is try to propose systems where you can enhance the separation of, for instance, CO2 or methane, or CO2 and nitrogen. At the same time, to choose the most appropriate geometries that can enhance this separation between those systems. So this can be done looking for the size effects, also the fluid flow, and finally the gas composition. Then what you see here is experiencing on virtual reality, but as a video, not the full immersive experience. And with a small carbon nanotube radii, we could see the structuring of the nitrogen molecules here. You also studied this with the nitrogen and also CO2. So this is one of the interaction of the nitrogen with the carbon nanotube is one of the talks in the poster sessions with Carlos Martins. At the same time, you can what would you like to see is how you can use the confinement in such a way that it can promote the separation of CO2 in the other gases. In this, on this idea, not only to look for the carbon nanostructures, but also looking for structures that has a porous media. No? This favor the confinement. At the same time, you can choose some functional groups that is able to selectively to have the CO2 absorption on that. And what you see here is also one of the work that is shown in the poster, where you could then try to understand how the CO2 or other molecules are going to interact with this open material. This is the ZIFs material. There's a kind of a metal-organic framework where, because of the choice of this functional group, you can induce the CO2 absorption in favor of the separation of CO2 regarding to other systems. Now, with that, you have been able to propose a way to have the CO2 capture. Now, one way to be to have the CO2 separation regarding to other gases, nitrogen or methane. Now you have another problem, that is what to do with the CO2. Now you can either mineralize for long term, or you can use it for other purposes. So then this is the point for the other topic that I would like to bring to you. That is, how can you transform CO2 in other products that of the industrial interest? And for this topic, I'm going to also introduce a new way to deal with this material design. That is using machine learning process where you can enhance this survey in terms of which materials can help us to transform the CO2 in other systems. Now, what is the point? What is the difficulty? Is one of the questions that you have to think about is how can you manipulate the CO2 molecule? Because this is a very stable molecule. And what you'd like to do is mainly to bring the CO2 molecule to the CO2 anion. So you want to bend this CO bonds here. And for that, you need to choose selectively. There are several ways to do so. One is either photo activation or thermal activation, plasma activation. But would you like to bring to you one example where you're going to use the electron activation in such a way that you want to bend the CO2 molecule and form this CO2 radical anion that will be the start point for transform CO2 in other products. This is a problem because you will not only want to be able to have this band, but selectively choose what is the window of energy that is needed in such a way that you want to transform CO2 for other kinds of systems, in particularly some systems that you'll be interested to use in the industry. Now, from the point of view of possibilities, you have explored some of the metal systems in terms of looking for the selectivity, at the same time to choose the right window we are going to transform the CO2 for the exactly system that I'm interested in. And here, what you have done is to try to convert CO2 in the oxalate. So this is more or less what the mission. So once that you have the CO2, you can include the CO2 in an electrochemical device, can be a fuel cell, for instance. And the correct choice of the catalyst here can select the view for a given product of the CO2. The problem here is from the material design that you have several parameters or features to look for. The catalyst, the solvent, the electrolyte, the applied potential, the temperature, the pH, and the pressure. So experimentally, you have to test every kind of situation to see if you're going to observe that selective product. Now, in this work, we introduce a machine learning model, and it has been published by yesterday. So this is a very fresh paper that you bring to you, and also was one of the posters by Álvaro. Now, what is the idea? Is to be able to, using the information coming from the database for materials, to produce a machine learning model that you can either have ideas about some of the properties, at the same time, think in terms of the catalyst predictions, and finally, to validate with the real DFT calculations and propose for the experimentalist to make the synthesis, and finally, to enhance the oxalate production. It has a very high value from the industrial point of view. So the goal here is to screen materials for looking for these systems by using the CO2 electron reduction using a model from machine learning. Now, you have implemented that to predict the energies, the adsorption energies for several systems that is interesting for this reaction to transform CO2 in something else. And this has been done by using, for instance, some database that is already available in terms of catalysis. So using this information, you end up with a machine learning model that allows us to predict the adsorption energies of these systems. And this has to do with several possibilities that you have in the database in terms of the reactants, the surface, what is the phases that you have it on these metals, the different these functionals that you may have it in the system to finally to be able to get the absorption energies. So would you like to make predictions on some important chemical species that can lead us to go to the oxalate, and also to use then the machine learning models in order to predict the energies, absorption energies of CO2 in CO. However, there are one challenge point that this anion is very hard or very difficult to calculate by first principle calculations. Now, the key point here to use the machine learning is we are not going to do the DFT calculation by itself, but we're going to have a model based on DFT that allows us to get information for even some species that was from first principle you cannot calculate directly. And this is more or less what we have here for the anion, the CO2 minus, absorption energies. This is the energies for the different metals, possibilities as a catalyst, with the different surface planes that you can have the absorption of CO2 there. You have done this using as parameters a lot of functionals. Does not mean that you have calculated by first principle calculations, but you have done a model that is able to capture some features by looking for these different functions. Now, what you can learn from this curve? Now, you could identify two separate regions, and also as the same trending regarding to the functional that you choose, because here you are not interested in the accurate absorption energy, but you want to see a screening of possibilities that you can use it as a catalyst. In the one, I'm going to finish already. So one point is this possibility to have the transformation of CO2 in CO, that is this left side. And the other one is regarding the CO2 to other products on this right side, where you have a higher, less absorption energy. So I just want to finish with this, because in the title you have molecular storytelling. No? Then I want to justify that. This is basically an idea where you're going to use, at the same time that I can use these tools in order to make the design of materials, also would you like to bring this for the general public, so people can understand what is going on in terms of greenhouse gases or other situations that happens in a scale that is very far from our daily life. And to do that, you mainly make interviews with people, prepare videos, and make the experiences on virtual reality. And with time, you have been able to produce content and make the invitation for next year. You can visit the USP. You are preparing a lab of immersion room in the molecularium, where you can make these experiences from the virtual reality point of view, using the other senses. At the same time, with the molecularium, that is the idea similar to the planetarium but from the molecular level, you also are able to experiment with other senses, like to listen, to be able to touch, and the other experiences. So I thank you with the time. I would like to thank all the people in our group, in the funding agencies, and thank you very much for your attention.
You just answered the question I was going to make in the last two slides. Are there any questions? Well, perhaps quick. No? So let's let's go to the next, and let's thank Caetano again.
Thank you.